Let us discuss a question from heat transfer. So basically it's a question on heat exchanger. A counterflow heat exchanger is given where the directions are reversed. Okay, so you have, let's say, this is where the water is going and the inlet temperature is given as 35, whereas on the outer, let's say, the oil is coming in the reverse direction. The inlet temperature of the oil is also given, which is 120. Okay, no other temperatures are given. The specific heat is given for both, and the mass flow rate is also given for the both. So thing is that now we need to find out what is the effective rate of heat transfer from the oil, because oil is the heated material. So oil to water, how much is the heat transfer that is taking place? Now these kind of problems where you don't have at least three temperatures, if you have two inlet and one outlet temperatures, then by just balancing the heat transfer from one to other, you can get the other temperature, and then you can get the heat transfer. Okay, but in these kind of problems where you have only the inlet temperatures, okay, in this kind of design problems you have to use the NTU method, because NTU we have the expression. Okay, and for this counterflow heat exchanger, the expression for effectiveness is 1 minus the, we always express in NTU method, you'll observe that we always have depending on the design, we always have a formula for the effectiveness, and the heat transfer is defined as effectiveness into the C mean into the difference in the temperatures at the inlet. Okay, so these class of solutions are useful for problems where you have only the inlet temperatures defined. So first of all, there are two things you need to find out: effectiveness, and effectiveness depends on, is a function of your NTU, which is heat transfer units, and also a function of C. Okay, so this C is nothing but C mean by C max, that is heat ratio of minimum heat capacity to the max heat capacity. So we need to get first effectiveness, and effectiveness formula for this design, well, is derived, and you got to remember, at least as per this problem. So minus NTU 1 minus C. Okay, as I said, it will be as a function of NTU and C. So 1 minus C EXP, that is exponential basically, minus NTU 1 minus C. So now first we need to get NTU and ratio of heat capacity. So first let's see what is C mean. What is heat capacity of oil and what is heat capacity of water, and then we will decide which is minimum. So heat capacity is mass into specific heat. So mass of the oil into specific heat of oil, and that is given as mass of oil is given as 1.5 into specific heat is 1.88. So this we'll get in kilojoules per second per Kelvin. So for the oil, when I multiply 1.5 and 1.88, I get, when I calculate, I get 2.82. So it's kilojoule per second, so it's kilowatt per Kelvin, right? And C of water is again mass of water into specific heat of water. Okay, so that is 0.8 into 4.182, that is equal to 3.34 kilowatt per Kelvin. So comparing, this will be C mean because it's the minimum of these two, and this is C max. Okay, so once we identify this, now the ratio C mean by C max we can directly get, because our formula is in terms of these. So C mean is 2.82 by C max, there is 3.34. So this ratio is basically 1.84, right? 0.84. Okay, so now what is NTU? NTU is again NTU is defined as UA by, it's a non-dimensional number, UA by C mean. So U is already given, the overall heat transfer coefficient is given as I think let's look at the problem. 350. So 350 net area of transfer is 15 by C mean is oil, which is 2.82 kilowatt. Okay, so into 10 power 3. Don't forget that. So when we do this, we get 1.86. So 1.86 is the NTU. So now we know C, we know NTU. We can directly use this expression to get the effectiveness. And effectiveness is, once we use this expression by substituting, we get 1 minus, let's substitute, minus 1.86 into 1 minus 0.84 is 0.16 by 1 minus 0.84 into e power minus 0.84, 1.86 into 0.84. So you have to just substitute, okay, in this expression. 1 minus okay, so at the top you have 1 minus e power minus 1.86 into 0.6. At the bottom you have 1 minus 0.84 into 1.86 into 0.84. Okay, so when you calculate this, you get a value of 0.684. Okay, so now you have to just substitute in the Q. So 0.684, we have the expression for Q. C mean is what we calculated, 2.82 into 10 power 3 because it's in kilowatt, and to the temperature difference, which is 120 minus 35. So when I calculate this, I get a value 163.95, okay, into 10 power 3, so it's kilowatt basically. 163.95 kilowatt is the answer. So remember that when you have inlet temperatures only, you have to use NTU, but only thing is, the problem with the NTU method is you got to remember the formula based on the design. Most of the time it will be provided, but at least for a counterflow heat exchanger, you got to remember it, 163.95. Thank you.